These big stromatolites are composed mostly of rock at the bottom, and the only living part of the stromatolite is a thin layer on top. And that thin layer on top is made up of microscopic blue-green bacteria called cyanobacteria.
Named after the blue-green color of their cells, these cyanobacteria use photosynthesis to collect energy from the sun. They secrete a sticky coating to shield them from ultraviolet radiation. As tiny pieces of dust and sediment settle on top of the sticky cells, the bacteria migrate closer to the surface to reach the light. The layers of sediment build up by about 0.5 millimeter a year. These structures contain living microbes, just as they have for thousands of years.
The amazing thing about these stromatolites is that the microorganisms which build them are so tiny. And the structures that you see around me, compared to their size, are enormous. It would be like if humans made a skyscraper that was 105 kilometers high by 70 kilometers across. These are massive structures for the size of the organisms that make them.
Many different shapes and sizes of what appear to be fossilized stromatolites have been found in the rock. It seems likely that these structures were formed by some type of microbe living on the early Earth. Perhaps even by the ancestors of today's cyanobacteria.
We're looking at sort of a cross-section through the top of these cones and the layers that were laid down year after year. And the fact that they're all different sizes on this one surface shows that there was a colony of microorganisms growing on this one bedding plane. And that's really fascinating because it means that life evolved on this planet very early and very fast.
And it's the cyanobacteria that would bring about the most astounding change in Earth's history. A change that could have started as early as 3.5 billion years ago. Over time, stromatolites would spread out across the planet. As a byproduct of photosynthesis, the ancient bacteria produced a waste gas, oxygen. The oxygen was absorbed into the oceans at first. There it combined with iron erupting from undersea volcanoes to form iron oxide particles that fell to the ocean floor. Over the next several 100 million years, the planet literally rusted. There may have been other forces at work, but eventually, all the iron was turned into oxide, building up layer after layer, one of the most valuable mineral deposits on Earth, iron ore. Located in Western Australia, this is one of the world's largest iron mines. The iron here was originally deposited on the floor of a primordial ocean.
Control Blast 2, we're at the firing position, stopper's connected. We'll fire in 10 seconds with a 5-second countdown.
Roger, Blast 2.
Every week they excavate 500,000 tons of iron ore, used to make steel for everything from cars to skyscrapers.
4, 3, 2, 1, fire.
In a more pristine state, thousands of ancient layers of iron ore are preserved in the Karajini Gorge, just 30 miles from the mine. The layers exist because different amounts of iron oxide were deposited at different times of the year. Cyanobacteria produced oxygen in varying amounts as water temperature changed with the seasons. All over the world, vast amounts of iron ore were laid down in similar ways. On our day-long clock, this process continued until 1 in the afternoon. Eventually, oxygen produced by cyanobacteria began to build up in the atmosphere. Slowly but surely, this transformed the planet. Over the next 8 hours or so, tiny microbes raised the level of oxygen from less than 1% to today's 21%. The time was about 9 p.m. It's amazing to contemplate, but without cyanobacteria, there would be no oxygen, and Earth would still be smothered in noxious gases. Plants, animals, and humans would have never evolved.
We're sitting here today breathing an oxygen-rich mixture of air. We couldn't be here without that oxygen, but that oxygen wasn't present on the early Earth, and it only became present because of the activity of photosynthetic organisms.
Life has made this environment what we know. It's allowed us to live on the surface. It allows us to breathe. It allows large organisms like we are to function at very high rates of activity.
The oxygen also helped protect life from the sun's lethal ultraviolet radiation by creating a layer of ozone in the upper atmosphere.
One of the fascinating properties of that is that it actually screens out, just sort of like a sunscreen does on your skin, screens out this harmful radiation.
With the protection of the ozone layer, life was able to diversify into more complex organisms. It took only the last 3 hours of the day for all other life forms on our planet to evolve. The first multicellular life emerged at 6 minutes past 9 in the evening. Then came fish and insects and reptiles. By about 10 minutes to 11 in the evening, dinosaurs roamed the earth. The first primates appeared at 20 to midnight. And with less than 30 seconds to go, the first humans made their appearance.
It's only been the last 10% of the Earth's history where there was life on the surface of the Earth that you would see with your naked eye. So for most of Earth's history, life has basically been invisible on the Earth.
Over 1 billion or 2 billion years, the amount of oxygen that these little creatures produced was enough to actually change the entire atmosphere of the planet.
Multicellular life that we're most familiar with, animals, plants, their environment was made possible by the slow, toilsome task of bacteria to oxygenate the atmosphere.
Microbes ruled the Earth for more than 3 billion years, 2/3 of its history. These tiny organisms had transformed an entire planet. Without them, complex life, humans included, would have never evolved.